Welcome back. 5.2, we're getting to the very first law of thermodynamics. You're going to learn the second and the third law when we get to part 2 of energy in chapter 19. Okay? This law is going to sound very familiar to you, and it really should sound familiar because you learned it in CP and honors. The first law of thermodynamics is that energy cannot be created nor destroyed. Well, if you can't create it or destroy it, then what do? You convert it, you conserve it, you rearrange it, you do whatever you want to it, but whatever you have in the beginning has to equal in the end. So we like to call that the energy of the reactants has to equal those energy of the products. So whatever you started with, you got to have the energy in the end. You can call it the law of conservation of energy, the first law of thermodynamics. Either one is fine. This also pertains to how potential energy can be converted into kinetics, okay, which was what we just talked about in 5.1. The first law of thermodynamics states that energy can't be created or destroyed, but it can be changed from one form to another. Now, we got to talk about two key vocabs when we're getting ready to talk about thermal chemistry, because we're getting ready to correlate how chemical reactions get into this. First, system and surroundings. If you're going to change it from one form to another, we have to figure out what is the part that we're studying and what is the part that we're not studying. So we call it the system. This is the part of the experiment that we are focusing all our attention on. In a balanced equation, it would be like the reactants and the products, okay? It'd be everything in your balanced equation. So I'm going to put right here, balanced equation. For right now, we're just going to do like everyday type life type of examples. We're going to get to the balanced equation part in the next video. So like the system, okay, would be this flask with the chemicals inside of it. So that would be my reactants and that would be my products, okay? If it's not in that container, everything outside of it is called the surroundings. So that means it's called everything else. This means it's not our focus, okay? It's the air, it's the desk, it's you, it's the thermometer, it's anything but not what we're focusing, okay? So the surroundings normally consist of the container and then everything outside the container. And like I said, this could even, when we get to the thermometer part, it's also going to be part of the thermometer. So if I have a box, okay, as you see right here, and you're going to notice a lot of the pictures coming up, it's a lot of boxes. If the arrow is going into the system, that means that the system, the energy is being gained by the system from the surroundings. So that means I'm going to get a positive energy change, okay? So if the energy is going into the system from the surroundings, because it's got to be converted from somebody, then that means I'm going to gain energy. If the arrow is pointing outward, that means that the energy is coming out to the surroundings. And that means my value, when I start calculating, my value is going to be a negative energy. Now remember, this energy is going to be in joules, no matter what, but it can be positive or negative. There are three types of systems that we like to study. The difference is between them, it's about energy versus matter. Okay, so for an example, an open system. An open system, you can have energy, as you see right here, the heat, okay? That's your energy that can come in or out. And the matter. The matter right here, okay, over time, doesn't water evaporate, okay? And that evaporation, that liquid, that mass changes into something else. So like if you have uncovered boiled water, the heat comes from the system into the system from the stove, and the water is released to the surroundings. So at evaporation, you have your liquid in here, but when that liquid evaporates, then it turns into gas, because the law of conservation says the mass, total mass, has to equal. It just got rearranged to something else. So because of that, energy is exchanged and matter is exchanged. So we call that an open system. Anytime we do labs when we're heating stuff up, it is always an open system, okay? A closed system means that you can only exchange heat, no matter. exchange. So we cover up the dish. We add a stopper, anything like that. That means the system does not lose or gain mass. Okay. So there's an example coming up of a piston. Like I said, like if we put a stopper on a flask, we would never heat up that flask with a stopper on it. But if we put a stopper on it, we can't have any matter exchange. But it can still get hot or cold. We can still exchange some energy. The only one that does no transfer of any, no matter and no heat, is something called an isolated system. Your guys's those thermal flasks that you have, Stanley cups, stuff like that. If you notice, you put ice in it in the morning, and usually when I go home and I'm cleaning out my flask, I still got a ton of ice still in my flask. It's still cold. So sometimes people put, that live on the East Coast, they'll put like hot cocoa in there or some hot soup, still hot by the end of the day, okay? Because it's able, that's why it's called insulate. It keeps the heat and the matter inside perfectly. So there is no exchange of it. So if you put coffee, hot chocolate, some soup in it, it's not a perfect isolation, but it's as close as we can get to no exchange of matter or energy. So this is the only one that has energy and matter that can be exchanged. This one, closed system, is only energy, and isolated is no exchange of any type of energy or matter. So when we're looking at these examples, we got to pay close attention to what type of system we're looking at. So from the first law of thermodynamics, when a system undergoes any type of physical or chemical change, the change in internal energy, okay, which energy we call E. Now change, this is a very important word throughout AP. Change means it's a triangle. And what that triangle means is if we take the final info minus the initial information. We like to also call it products minus the reactants, okay? So we call it a triangle E, and sometimes in math, that triangle is called a delta, okay? I always call it delta because that's how I learned it back in math. Given that heat is Q, is added or released, so if you add heat or release heat, positive or negative, from the system, plus the work, so plus, we're going to be adding two numbers, plus the work done on or by the system. So our work can even be positive or negative. So we have a very simple equation, Q plus W, and that Q plus W, all units have to be the same because you're adding numbers together. We like to use joules, but you can also use kilojoules, just as long as they're joules of some sort, okay? So when we're relating this delta E to Q and W, first, let's make sure we understand those definitions of Q and W. So force, it's a force that we apply to either push or pull an object, okay? Work is the energy used to move that object against a force, okay? Like lifting that bowling ball. You are putting work into it to move it up. Heat is the energy transferred from system and surrounding. So remember, it's just going back and forth because of temperature change. Okay, so you're going to see this delta T coming up also, which means final minus initial. And then the change in energy is the capacity to either do work or transfer heat. So as I said, you can have positive and negative values, but be very careful with the wording. If your Q is positive, that means your system gained heat. So as I said, when you start looking at these boxes, you're going to get an arrow that looks like it's coming in, and the box represents the system. Okay? So in that system, if it's gaining heat from the surroundings. Okay? It's always gaining from the outside. Okay? If Q is negative, that means it's losing heat. So that means your arrow's coming up. But who is losing it? The system's losing it to the surroundings. So that means that your heat is going to the surroundings. Okay? If your W is positive, that means you did work on the system. Same thing, your arrow would be coming in. And if you did work by the system to surroundings, same thing, your arrow's going out. When you add these two values together, if your answer is still positive, that means that the reaction had a net gain in energy. The system had a net gain. But if in the end your answer is negative, nothing wrong with that. That means you had a net loss in your system. So let's look at an example. Inside engines, there's something called a piston. And in this piston, it goes up and down as much energy as you give your car, aka gas, speed, so forth, so forth. So if I have water, which there's water obviously inside a car engine, we always got to put water in it. H2 and O2 as gases are confined inside that piston and are arranged as you see in the figure to the right. As the reaction occurs, the system loses 1150 joules of heat to the surroundings. Well, that just told me a lot. So we're talking about heat here. So that means my Q is 1150, but my system lost to the surroundings. So that means I got a negative joules. So beware of the positive and negative when you're reading. Because just because the number looks like it's positive doesn't mean it's always going to be positive. When this piston moves downward as the gases react to form water, as the volume of the gas decreases under constant pressure, and this constant pressure is going to mean something when we get to this next video, the surroundings do 480 joules of work. Now I know my work, but the question is it positive or is it negative? The surroundings do 480 joules of work on the system. On the system, which means my work, the surroundings are doing work on the system. That means my work is positive. No, you don't have to put the positive. I like to put it so I can keep track. So my W is coming in 480 joules, but my heat is coming out. So with heat, not only is it an arrow, but it's an arrow that's twice as big because it's not the same quantities. So when you draw your arrows, make sure that the size, and we call this magnitude, okay, is correct in sizing, okay? So my Q is coming out as my work is coming into the system. What is the change in internal energy? So I'm solving for delta E, okay? I want the change in energy. So when I write my equation, Q plus W, I have my two values. Nothing difficult about adding two numbers. The only thing I want to make sure, okay, I'm making a little note, sig figs. When you are adding or subtracting sig figs, remember it's the least after the decimal. Okay, after, not before. Okay, so because neither one of these have anything after the decimal, I'm going to plug in negative 1150 plus 480. Now, if you don't get the answer, negative 670, you may not have hit the right button. This negative right here on your calculator, it should be a button down at the bottom by the decimal button. And then you have your 0 button right there. So your negative should be somewhere at the bottom, okay? Not over on the right side next to the addition. That's called subtract, okay? So that means that the overall energy, the overall system, had a net loss in energy. You do not have to explain unless AP asks you to explain. So because it's negative, you had a net loss in the system in regards to energy. Okay? Very, very simple math equation. Let's do two more. What's the change in energy? So I'm looking for delta E. For a process in which a system absorbs 140 joules of heat from the surroundings. Absorbs, the system absorbs. So my Q is positive. Okay, so if I did a diagram, that there's my system, and I'm going to make it a closed system, I'm going to make sure that my Q is coming in, and it's 140. And it does 85 joules of work on the surroundings. Well, it's not going in the system is giving it up. So it's giving up negative 85 joules of work. So that means my W is coming out, but it's a smaller quantity. So my arrows would have a different size. So I'm going to write my equation, delta E, Q plus W, 140 joules, plus, if you want to say a negative 85, which really means you're subtracting, so 140 minus 85, nothing after the decimal in this case. So in the end, I'm going to get a positive 55 joules, which means the system had a net gain in energy. Okay? One more. What if we calculate the change in energy when a bar gold is heated and absorbs 322 joules of heat? Well, the bar gold is the system, and it says it absorbs 322. That means the gold is getting heated up. The gold is the system, okay? So because the gold is the system, my Q is going to be positive, okay? But what about work? If there's no mention of what happened to work, then that means work is 0. Makes it even simpler. Q plus W, work is 0. That means in the end, nothing really show up adding. My delta E, 322 joules. And that means my system had a net gain, okay? But when we have these gains, usually temperature is changing, okay? So here is our first learning objectives, has to do with endo and exo, okay? Now, when you refer to endo and exo, it can only be referred to Q, okay? Not energy, okay? To Q, because this has to only apply to heat, okay? So in our learning objective, 2.A, explain the relationship between experimental observations and energy changes, delta E, associated with a chemical or physical change. So temperature changes in a system, and it indicates energy change. So when you change the temperature, you're going to also change energy. Okay, whether it's positive or negative, we need some numbers. Energy changes in a system can be described as either endo or exo. So if it's endo, that means my Q is going to be positive. And if it's exo, that means my Q is going to be negative. Such as heating or cooling a substance, phase changes, or chemical reactions, transformations. When a chemical reaction occurs, the energy of the system either decreases, exo. So if my energy decreases, it's probably because my Q was negative. Or if it increases energy, probably because my Q was positive, okay? Or remains the same. Well, if it remains the same, then that means my delta E is going to be 0, okay? So what does that tell me? That means my Q and W are the same value, but one of them is positive and one of them is negative. So for exothermic, the energy lost by the reacting system, species, is gained by the surroundings. So if it's exo, so remember, it's coming out. And if it's endo, I'll do it in a different color. If it's endothermic, the system gains from the surroundings by heat transferring or by work being done on the system. The formation of a solution may be exo or endo depending on the relative strength of the intermolecular forces. We've talked about that, IMF, okay, aka chapter 11. Interactions before and after the dissolution. Dissolution is a fancy way of saying dissolving. So think about when salt hits water and I'm breaking it up into those ions, there is a temperature change. You don't realize there is, but there actually is. It's a small change, but there is. So we're going to do a lab with that where we're going to put different salts in water and give it a little stir, and we're going to see how temperature changes. So when you dissolve salts, okay, there is a temperature change, whether it's positive or negative. Every salt is different, okay? So we look at that when we look in chapter 11, intermolecular forces. So I want to give you some everyday example with like exo versus endo. So exothermic, our Q will be negative. And as you see, all that heat is coming out of the system. So I'm sure you've used like a hot pack sometime in your life, especially if you're an athlete, you work out. And when you crack those hot packs, you put it on those sore muscles and you feel that heat. That energy in the form of heat is transferred from the system to the surroundings. So my Q is negative because my surroundings is gaining it. You feel warmth, okay, because it's giving up that heat. When we touch it, because our hands are the surroundings, okay? So remember, when you are grabbing it, and don't make fun of my beautiful drawing, making sure you had 5 fingers there, okay? Your hand is the surroundings, okay? So your hand gets warmer. And then eventually that cold pack will die and then your hand will cool back down. So like when it's a cold day, we like to hold like a cup of coffee because it makes our hands feel very warm. Well, sometimes doctors even tell us when we have sore muscles, we got to use hot and cold packs because maybe those muscles just are too inflamed where you need to rotate the hot and the cold. So in this case, the heat is going from the surroundings to the system, okay? That means my Q is coming in. So all this heat that's coming in, the outside is hotter, but now these cold packs are nice and cold, okay? So there was a demo last year that 2 gentlemen in honors did. I'm gonna give a shout out to Roberto and his brother, where they used a cold pack for their demonstration of the, it was the fire, I can't remember the actual name of the lab, but it was the fire one where they used cold packs as the salt instead of ammonium nitrate. So what they did was in that cold pack, when they opened it up, if they would have actually added the water that came with the pack, they would feel cold, okay? So all that heat coming in, the surroundings to the system, you would actually feel coldness when we touch it because our hand is part of the surroundings. So you would feel all nice and cold with that hand. So like if we ever put like ice in our hand, because our hand is warmer. Oh my goodness, that is some weird hands there. This is why I find pictures on the internet instead of drawing. So if we have this nice ice cube, aka our system, okay, our hand is actually considered very hot compared to that ice. And all that heat from our hand is coming in. And what's going to happen to that water ice solid? Well, it's going to change into water liquid. Okay, and we call that melting. Okay, that's why it's called melting ice. Okay, so in a chemical reaction, exothermic, the energy is released. In an exothermic reaction, that's where our Q will be negative. So when you feel that beaker, it's going to feel hot to you. Because remember, your hand is part of the surroundings. If it was an endothermic process, we're going to absorb heat. So that means when you feel it, feel the beaker, it's going to feel cold to you. Okay? Because all the heat is coming in. So there is an always rule. Heat will always flow from hot to cold, okay? Notice right here your hand. The hot hand heat is flowing to the ice. The hot cup of coffee, is flowing out to your hand, okay? Heat will always flow from hot to cold, always, 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 okay? So in an exothermic reaction, energy is released into the surroundings. Heat is released, that's why we know it's negative, and work is done on the surroundings. So our W, because it's being done on the surroundings, our W is going to be negative. As the result, the temperature of the surroundings actually increases. Now notice it says of the surroundings, okay, not the system. So remember right here, initially the surroundings was cold, okay? But as soon as that heat is released and it's coming out, it's actually warming up the surroundings. So that temperature before and after, that after temperature is actually warmer than what it started with. In regards to endothermic, energy is absorbed. So I'm going to get that positive energy. Okay, same thing over here. I should have said negative energy. The heat is absorbed. So my Q is going to be positive. Work is done on the system. So work is positive. So in the result, as a result, the temperature of the surroundings is actually going to decrease. Okay, so remember, the surroundings was hotter. And all that heat came in here. And because the heat is leaving the air, in the end, the air is actually a little cooler. Okay? So you're going to notice this because when we do these labs with salt, I'm going to ask you to, hey, put your hand, what do you feel? Use the back of your hand to touch. Is it hot or is it cold? Okay? So with this chapter and the chapters coming up, energy is the star of the show. So we got to make sure we pay attention to what's happening to Q, W, and temperature. Okay? Last thing is you saw this in chapter 14 with activation energy graphs. Okay? If you have an exothermic reaction, exothermic means we lost heat from the system to the surroundings. So right here, that was that change where you started with higher heat and you ended with cooler heat. That's how you knew that your delta E was negative, okay? You had a higher value and it went down to a lower value. Sometimes graphs label this delta H, which we're getting ready to talk about in the next video what delta H is, okay? Right here, if you started right here, which is a lower value in energy, and you gained heat or energy, then you have this higher energy in the end, because look at who's on the y-axis. Potential energy, energy of position at a point in time. Okay, it's not kinetic energy, it's potential energy. So because you gained energy, then that means your energy is positive. So your delta E is positive, and because it's endothermic, our Q is positive. So lastly, one more time, when you're dealing with exo and endo, you can only use exo and endo when referring to Q, not energy and not work. Okay? See you on the next one.